Hi, my name is Eiji Hayashi. I'm a technical lead at Google ATAP. ATAP represents Advanced Technology and Project, which is essentially the research section for the Google hardware product. And then we are doing working on crazy technologies, which could take years to launch. So today we'd like to talk about the nonverbal interaction using Soli data. Soli data is one of the sensors which actually we have been working on about 5 years at ATAP. And we released some of the product. And now today we'd like to talk about more about how we can enable nonverbal interaction, which is a very important aspect of human-to-human communication using such sensor. So we actually have so many smart devices around us. But we actually wondered, are they actually smart? The reason being, when we think about human-to-human communication, there are lots of things which we can do without actually asking without explicit request to each other. For instance, if she has a pen and I extend my hand to her, she naturally passes the pen to me. Or when I look at that direction, the other people in the same space, like you, will look at the same direction and then paying attention to what I'm paying attention to. This is pretty natural in human-to-human communication. But none of our smart devices can do it. Smart devices are just sitting there until we touch it, like touch screen or switches, or maybe we say the verbal command, like OK Google or Alexa or Siri, to give explicit command. And we wonder, what if device understood us in the same way as humans understand each other? So to answer this question, we actually approached the question from both technology and design perspective. That's why in your team, the engineers and designers are working pretty closely to answer this kind of pretty complicated interaction problem from both technology and design perspective. Now let me talk about this problem from technology perspective first. From technology perspective, we can rephrase this question into, can we create a sensing system that makes device aware of what's happening around them? Because if devices are not aware of what's happening around them, it is impossible for them to respond to these things. So the first question is, can we actually make a device aware of what's happening? We can actually easily do it using camera, because camera is a great sensor, which gives us a lot of information. But in some contexts, we may not want to use camera. For instance, in our personal space, probably we don't want to put camera in an always-on manner, at least. Now, we saw what sensor is available to achieve this goal. And we found that actually radar is a pretty good candidate for this sensor. Radar is at least the more privacy-preserving compared to camera, because it doesn't capture the images. And it works through materials so that we can put sensor behind the wallpaper or maybe enclosure of the devices. And it also has many properties which is really great for this use case. But the only problem is it was actually huge. So this is a radar which tried to capture the airplane, but probably we cannot put this into device or even in our room. Then we shrinked it. So this is our radar sensor, which is roughly 3 millimeter by 4 millimeter, and it has 4 antennas. It doesn't have a mechanical steering system. The standard radar, we can steer the radar like this and then scan the environment. This chip doesn't have any mechanical system, so that it's easier to integrate the device. But it actually makes it difficult for us to make sense of what signal we are seeing. So for instance, this is what radar is seeing, and then for reference, what camera is seeing. There is a person moving away from a sensor, and then after that, there's a dog running to the person. As you can see, from radar signal, we can somewhat see that some object is moving away, and then another object moving away as well. While we can see the context clearly from the camera, radar is really kind of ambiguous, which is good from privacy perspective, but again, which is bad from the signal processing perspective, or make sense of these signals. And we are working on building algorithm which actually makes sense of this complicated signal. We started from understanding fine finger motion, like this. So as you can see, the radar sensor is pretty sensitive to fine motion, and we can capture these finger motions using the radar sensor, which may be good for the AR/VR context as a controller. We can detect these like tiny motions, which can reflect it to the AR/VR context. Also, we created something like this, like that understand our arm motion. This algorithm allows us to interact with the device, which is out of our reach, without approaching to the device. And without saying, okay, Google, which is great. But at the same time, we found that actually using exactly the same sensor, we can detect a lot of different body cues. For instance, this is the first one. The sensor detects whether a person is nearby or not. And based on whether a person is nearby or not, for instance, we can turn on and turn off the display or make the device ready for the interaction. Along this line, we start understanding the person's position in 2D space. In this example, on the left-hand side, that's what radar sees. And then there is a signal processing pipeline, which consists of the machine learning, heuristic, and rule-based algorithm. And eventually, we get two-dimensional position of the person from bird-eye view, and then understand whether the person is approaching, moving away, or standing still in that space. In more recent work, based on the radar image at the top, that's the input to the system, we can understand where our body segments are in 3D space, like head, torso, and hand, and then orientation of these head and body segments. That actually gives us more information about what people are doing, where people are paying attention to, and what their intents are. So now our design lead, Lauren, can talk more about how we utilize those signals in the design context to create the interaction language for nonverbal communication.
Thanks, Eiji. So as Eiji said, at Google Advanced Technology and Projects Group, we work very iteratively between technological invention and design innovation. And based on these algorithms that Eiji explained around how people move through space, our team wanted to understand how might we create an interaction language around this that's inspired by nonverbal communication, or the way that we naturally speak with each other. And one way that we naturally mediate interactions with each other is through proxemics. So one of the most well-known examples of this is Edward Hall's theory of proxemics, where he looks at how people perceive, interpret, and use space, with an emphasis on varying distances between people. So he identified 4 different zones that were reflective of our interpersonal relationships. And these are intimate space, personal space, social space, and public space. And this idea of proxemics or proxemic interactions have existed within human-computer interaction for a while now, and many examples, even from the academic community, date back to early 2000s before touchscreens. This example from 2003, called Hello Wall, uses discrete zones around the display to allow for a progression of ambient information to notifications to even direct interactions. And the main idea here is that varying distances between the display result in different types of interactions. But our team was wondering, is proximity alone really enough? Because the way that we naturally move in spaces is very nuanced, and we move in very different ways. So we were wondering if there was a way to better understand movement in a way that could help us anticipate and sequence interactions with computers. So curious about this question, our team conducted what we call interaction studies. And this is essentially where we take a spatially aware technology, such as radar, and we visualize it in different ways to really understand what sort of movements we can detect. And we discovered something interesting. We identified 3 different dimensions of movement that we think are critical in order to build spatially aware systems for computing. And these are proximity, so distance between me and a device, orientation, so the angle of my body or head relative to the device, as well as pathways or certain trajectories you may have in space. And this led us to create a theoretical framework based on the spatial relationships between people and devices. So our theory states that each one of us has our own personal space, and this is approximately, within arm's reach. And we think of this space as actually dynamic, so it can expand and contract based on my context and where I am. So, for example, if I'm standing here, this personal space may hug closer to my body. But if I'm walking, it may expand in the direction of my trajectory. And just as we have our own personal space, we imagine that the device can also have its own personal space that can also expand and contract based on the information or notifications or things it has to tell you. And based on these dynamic zones, we think that the overlap of these zones may actually carry some significance around the level of interest or engagement you may have with a person or device or object in space. And because we work very iteratively between technology and design, we wanted to really put this to the test and create a working prototype of this idea. So we wanted to test this theory of dynamic zones around a user and a device. And there's a few scenarios here. So on the left, you can see an example where I'm close to the device, but I'm just walking by. So you don't see a lot of overlap there in the magenta. But conversely, if I'm approaching the display, walking towards it, you can see that there's a larger amount of overlap there. And we can almost, when the zone expands, we can almost anticipate the moment right before you interact with the display. And we think that this percentage of overlap is actually a key component that we can use to spatially mediate interactions with devices, in the same way that we use nonverbal cues to begin, maintain, and end conversations. And from this, we created a set of interaction primitives. And these are all inspired by the natural way that we communicate with each other spatially. These are approaching and leaving a device, turning towards and turning away from a device, passing by a device, and also glancing over at a device. And similar to how we use taps and swipes on our touch screens, we think of these as actually fundamental building blocks that we can use to reconfigure and recompose new use cases for products and experiences. So a few examples. First, we can use turning towards and away from a display to actually play and pause media. So let's say I'm, cooking in the kitchen, maybe my hands are wet or messy, and I walk over to the other side of the kitchen to grab another ingredient. The device can be considerate in that moment and actually pause the display, only to play the display when I have come back over, I'm turned towards the device, and I'm ready to engage with it. We could also use things like glance to reveal notifications. So let's say I'm in my home, I'm reading a book, enjoying my Saturday morning, and a notification comes in from the device. It can first kind of get my attention with an audio cue, for example, but let's say I want to finish what I'm reading, finish the page. It's not until I glance over at the display that it could actually expand that notification and give me more information. And we can also use approach to reveal notifications. So let's say you're about to leave the house, you're gathering your items, and you're about to walk out the door. And the device understands that, you're about to leave the house and it may be raining in 15 minutes. So in this moment, the device could, remind you to grab an umbrella before you leave the door. And all of these examples of interactions that we're working on, they just kind of scratch the surface of what we can do with this theory and these interaction primitives. But the main idea here is that it points to a future in which technology actually feels more calm. It recedes into the background, it understands your context, and it only comes to the foreground when it's needed. This means spending less time tapping and swiping on our phones, configuring and managing each device, and more time present in the physical world with each other.
Great. So as this example shows, in your team, designers and engineers are working pretty closely. And then technology-inspired design and also design question technology. And we are doing the pretty quick iterative loop to push this space forward. And we believe that through this effort, we can make the device aware of what's happening around them, and also make them understand the users in the same way as we understand people, to make the interaction a lot more natural. Thank you.